Let's review how to solve Newton's second law problems. 1. Draw a correct free body diagram. Don't forget any forces. 2. For direction A, write the sum of the forces equals the mass times the acceleration in direction A. If there is a surface, direction A should generally be the one perpendicular to the surface. Solve for whatever you can. 3. For direction B, write the sum of the forces is equal to the mass times the acceleration in direction B. Solve for whatever you need to. You will probably be able to substitute in something you solved for in the first part. 4. You should be done. Round your answer properly and make sure it has the correct unit, if any. In particular, coefficients of friction don't have units. Alright, let's try this one. We've got a mass, and it's moving to the right horizontally, and it's acted upon by some Newton force that's inclined up and to the right at some number of degrees above horizontal. So I've drawn that in the picture here. We have our mass, it's on a horizontal surface, it's moving to the right, and it's acted upon by some applied force at an angle so many degrees above horizontal. The coefficient of friction is given, and we want to find the acceleration of the mass. Step 1 is to draw a free body diagram, which will look something like this. We'll have the weight acting downward. Friction will act to the left because the mass is moving to the right, and friction always opposes the motion. This applied force is neither parallel nor perpendicular to the surface. As such, it is a rather inconvenient force, and so what we need to do is resolve it into its parallel component and its perpendicular component, which is why I've drawn those vectors like so. And finally, there is a normal force holding the mass up. It is very important to make sure that when we draw a free body diagram, we get all the forces, and as best we can, we put them in the right orientations. Now, let's write a Newton's second law equation. Typically, if there's a surface, we want to start with the forces that are perpendicular to the surface. And as you can see from the free body diagram, there are 3 of those. The normal force, the weight, and what I've called F perpendicular. I'm going to choose up as positive, so Fn acts upward, F perpendicular acts upward, and mg acts downward. And that is the sum of the forces, and that should be equal, according to Newton's second law, to the mass of the object times the perpendicular acceleration. Let's write another Newton's second law equation, this time using only the parallel forces. Again, we have to choose a direction to be positive, so I'm going to choose to the right to be positive. F parallel minus mu sub k Fn. That sum of the forces should equal the mass times the acceleration parallel to the surface. The acceleration perpendicular to the surface is 0. This mass will not jump off the surface, nor will it accelerate into the surface. So the whole right side of this top equation becomes 0. And we're looking for that as our final answer. We know what the mass is, we know what g is. We would be able to calculate F perpendicular, because what would F perpendicular equal? Wouldn't it be Fa times the sine of theta? So all of that is known, which means we can calculate the normal force and put that in right there. So we know the normal force. We know F parallel, because we could calculate it. F parallel would equal Fa times the cosine of theta. We know what mu sub k is, it's given. We know what the mass is. There you go. Solve that equation algebraically for A. If you had the numbers, you'd put the numbers in, and you're all done. A blank kilogram mass hangs vertically at rest from a spring. If the spring displaces so many centimeters, find the force constant. So here's our mass. We're going to draw a free body diagram. We've got the weight acting downward and the force from the spring acting upwards. This mass is at rest. the weight is numerically equal to m times g, and the force from the spring, according to Hooke's law, is equal in magnitude to the spring constant, or the force constant, times the displacement. I've left the negative sign off because that's taken into account by the direction of this elastic force, upward, opposing the weight downward. Let's write a Newton's second law equation. We only have to write one because there's only an up-down direction. There are no left-right forces on this mass. If upward is positive, then we're going to write k delta x, which is positive. mg points downward, so we say minus mg, and by Newton's second law, that sum of the forces should equal the mass of the object times its acceleration. Well, this mass is at rest, so the right side of this equation goes to 0, so we can write k delta x is equal to m times g. We know what the displacement is. That's given in the problem. We know what the mass is. We're going to assume that we're on Earth, so we know that g is 9.81 meters per second squared. We solve that for k. Here we've got a mass at rest on a horizontal surface. A rope is tied to the mass, and it has a certain tension, and it's angled so many degrees above horizontal. I've represented that in the picture here on the right. Also, a so many Newton force presses the mass into the surface. That's this applied force, pressing the mass into the surface. Find the normal and the friction forces. Clearly this is going to be static friction because the object is at rest. So let's draw a free body diagram. There's the mass, there's the applied force, there's the weight. Notice that I've taken the tension and I've broken it into a parallel to the surface component and a perpendicular to the surface component. The parallel component would be t times the cosine of theta. The perpendicular component would be t times the sine of theta. The normal force is going to act upwards, and friction is of course going to oppose any motion that we're going to try to impose on this mass. So let's sum the forces perpendicular to the surface. T sine theta acts upward. I'm going to choose upward to be positive. The normal force acts upward. The applied force acts downward, and the weight acts downward. And the sum of those forces should equal the mass times the acceleration perpendicular to the surface. This mass is at rest, so there is no acceleration perpendicular to the surface, so the right side of this equation becomes 0. For the parallel direction, if I choose to the right to be positive, it really doesn't matter. I have t cosine theta going to the right and static friction going to the left, and that should equal the mass of the object times the acceleration in that direction. Well, the mass is at rest, so again, the acceleration parallel is going to be 0. So now we need to find the normal force and the friction force. We know what t is, that's given. We know what theta is, that's given. We're given the applied force. We know what the mass is, and we know what gravity is. Everything is known. We simply solve those two equations, and we'll have our normal force and our friction force.